300 horsepower. That's what separates winning from watching in top fuel drag racing. In 1992, one Louisiana mechanic found that power hiding in the most unlikely place, the teeth of a pulley. Dale Armstrong didn't just break the rules, he exploited a blind spot so obvious that nobody else had even thought to look there. Picture this. It's summer 1992 at a drag strip in Texas. The air is thick with nitromethane fumes that burn your eyes and throat. Two top fuel dragsters line up at the starting line, 8,000 horsepower machines that can accelerate from 0 to 330 miles per hour in under 4 seconds. The Christmas tree lights drop. Yellow, 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 green. Both cars launch with a violence that hits you in the chest from a quarter-mile away. But something's different about one of them. The engine note is higher, angrier, like it's screaming at a frequency that shouldn't be possible. That car crosses the finish line 3 car lengths ahead. Outstanding in the pits afterward, crew chiefs crowd around the winning engine, trying to figure out what just happened. They check the blower, standard 1471 unit. They examine the fuel system. Nothing unusual. The camshaft, the headers, the clutch, everything looks regulation. But somewhere in that aluminum maze of precision parts, Dale Armstrong has hidden an advantage worth 300 horsepower, and it's sitting right there in plain sight. This is the story of how a mechanic from Louisiana outsmarted the entire NHRA rulebook with a modification so simple, so elegant, that when competitors finally discovered it, they couldn't believe they'd missed it. Armstrong didn't invent a new supercharger or discover some exotic fuel additive. He solved a problem that every top fuel team in America was struggling with, and he did it by borrowing technology from industrial conveyor belts. And to understand Armstrong's breakthrough, we need to understand the brutal physics of top fuel drag racing in the early 1990s. These weren't just fast cars. They were controlled explosions on wheels, burning through 15 gallons of nitromethane in a single quarter-mile pass. The engines operated at the absolute edge of mechanical possibility. Connecting rods stretched like taffy under load. Cylinder heads lifted off the block despite being held down by bolts torqued to 190 pound-feet. Spark plugs melted into glowing embers after a single run. And at the heart of these monsters was the supercharger, specifically a Roots-type blower that could move 900 cubic feet of air per minute. These weren't the polite superchargers you'd find on a streetcar. A top fuel blower consumed 900 horsepower just to turn it. Think about that. The blower alone required more power than a NASCAR engine produced. But it was worth it, because that blower could cram enough air into the engine to support combustion of nitromethane at rates that would have seemed like science fiction just a decade earlier. Here's where Armstrong spotted the problem everyone else had accepted as inevitable. The supercharger was driven by a reinforced rubber belt, essentially a giant timing belt on steroids. As teams pushed for more power through the late 1980s and early 1990s, they kept spinning the blowers faster. More blower speed meant more air. More air meant more fuel. More fuel meant more power. Simple equation, except for one thing. The belt couldn't keep up. Starting at 8,000 RPM blower speed, the belt was traveling at over 150 feet per second. The acceleration forces were so extreme that the belt would actually slip on the pulleys. Not dramatically. We're talking about microseconds of slip that you couldn't see with the naked eye. But those microseconds added up. Testing showed that at maximum load, the driven pulley, the one on the supercharger, was actually turning 10 to 12% slower than it should have been based on the drive ratio. That slip was costing teams 300 to 400 horsepower, and everyone knew about the slip. It was just accepted as one of those unsolvable problems in racing. Teams tried everything. They experimented with different belt compounds. They increased belt tension until the load started breaking crankshaft snouts. They even tried running multiple belts, but the packaging constraints made that impractical. The consensus was that 2,200 horsepower was about all you could reliably extract before belt slip became the limiting factor. That's what made Armstrong's solution so brilliant. He didn't try to fix the belt. He fixed the pulley. NHRA. Armstrong's background wasn't typical for a top fuel crew chief. Before racing, he'd worked in industrial automation, designing conveyor systems for manufacturing plants. In that world, timing and synchronization were everything. A conveyor belt that slipped even slightly could throw off an entire production line. So industrial engineers had developed specialized tooth profiles for timing belt pulleys, profiles that provided maximum grip without excessive wear. These weren't the rounded automotive-style teeth that racing teams were using. They were precisely machined profiles with specific pressure angles and root radiuses designed to mesh perfectly with the belt's teeth. One night in his shop in Louisiana, Armstrong was staring at a worn supercharger pulley, running his fingers over the polished teeth where the belt had been slipping. The aluminum was actually glazed from the friction. That's when the connection hit him. Why were they using automotive pulley profiles for something that had more in common with an industrial conveyor than a car engine? He pulled out his machinery's handbook and started looking up specifications for industrial timing pulleys. What he found changed top fuel racing forever. The standard automotive pulley tooth profile used in drag racing had a 20-degree pressure angle with relatively shallow tooth depth. It was designed for smooth engagement and quiet operation, perfect for a street car, terrible for transmitting 900 horsepower through a rubber belt. Industrial timing pulleys used a 14-degree pressure angle with deeper tooth engagement. The difference might not sound like much, but it changed everything about how the belt gripped the pulley. Dale Armstrong didn't just copy an industrial design wholesale. That would have been too obvious, and besides, he needed something optimized for the specific loads and speeds of drag racing. He spent 3 months in his machine shop cutting different tooth profiles and testing them on a dyno. He tried 12-degree angles, 16-degree angles, different root radiuses, varying tooth heights. Each iteration got a number and went into a notebook with detailed measurements of belt temperature, slippage percentage, and power transmission efficiency. The breakthrough came with prototype number 23. Armstrong had combined a 14.5-degree pressure angle with a tooth depth that was 15% greater than standard and a root radius that perfectly matched the belt's tooth profile under load. When he tested it, the belt temperature dropped by 40 degrees Fahrenheit, indicating dramatically reduced slippage. The dyno showed something even more impressive. The supercharger was now spinning within 2% of its theoretical speed. He'd eliminated 90% of the belt slip. But here's where Armstrong's genius really showed. He didn't just make one pulley, he made a set, both drive and driven pulleys with matched profiles. He also discovered that the tooth timing was critical. The pulleys needed to be clocked so that the belt teeth engaged both pulleys at exactly the right phase relationship. Get it wrong by even one tooth, and you'd actually make the slippage worse. Get it right, and the belt locked onto those pulleys like it was glued there. The first track test was at a private session in early 1992. Armstrong installed his custom pulleys on Kenny Bernstein's top fuel car, the same car that had recently become the first to break 300 miles per hour. With the standard pulleys, the engine was making 2,180 horsepower on the dyno. With Armstrong's pulleys and no other changes, same belt, same blower, same fuel system, it made 2,510 horsepower. The increase was so dramatic that Bernstein's crew thought the dyno was malfunctioning. They recalibrated it 3 times. The numbers were real. But horsepower on a dyno is one thing, making it work on the track is another. The first full pass with the new pulleys nearly ended in disaster. The engine made so much power that it overwhelmed the clutch settings that had been carefully developed for 2,200 horsepower. The car hazed the tires all the way through first gear, something that hadn't happened in 2 years. They had to completely recalibrate the clutch management system to handle the extra power. It took 6 more test passes before they found the right setup. And when they finally got it sorted, the advantage was devastating. At the 1992 NHRA Summer Nationals, Bernstein's car was consistently 2 to 3 hundredths quicker in the first half of the track, an eternity in top fuel racing where races are decided by thousandths of a second. Other teams noticed immediately. After each run, crew chiefs would casually walk by Bernstein's pit, trying to spot what was different. They checked everything: the injector nozzles, the blower intake, the exhaust headers. The pulleys were right there, bolted to the front of the engine, but they looked normal enough that nobody gave them a second glance. Armstrong was smart about keeping the secret. He had the pulleys anodized black to hide the machining marks that might give away their unique profile. He also made sure that the pulleys were never removed when other teams were around. If they needed to change a belt, they'd roll the car into the trailer first. When other crew chiefs asked about their newfound power, Armstrong would credit improvements in clutch management or fuel mixture. Technical half-truths that sent competitors chasing ghosts. And the NHRA rulebook in 1992 was incredibly detailed about superchargers. It specified the size, the rotor configuration, the case material, even the drive ratio limits. But nowhere did it mention anything about pulley tooth profiles. As far as the rules were concerned, a pulley was a pulley. Armstrong hadn't broken a single rule. He'd found a loophole that nobody knew existed because nobody had thought to look for it. And for 6 months, Armstrong's pulleys remained a secret. During that time, Bernstein's team won 7 national events. Other teams were getting desperate. Don Garlitz, the legendary Big Daddy, personally offered Armstrong $50,000 for the secret. Armstrong politely declined. John Force's crew chief tried a different approach, suggesting a pause technology partnership where they'd share innovations. Armstrong wasn't interested. He knew the value of what he'd created, and he wasn't about to give it away. The secret finally came out in the most mundane way possible. At the U.S. Nationals in Indianapolis, a photographer from National Dragster magazine was shooting detail photos for a technical article. He happened to catch the pulleys at just the right angle, with just the right lighting. When he looked at the photos later, he noticed something odd about the tooth profile. It didn't look like any automotive pulley he'd seen before. He showed the photos to a veteran crew chief who immediately recognized the industrial-style profile. Within 2 weeks, every top fuel team in the country was on the phone with pulley manufacturers, trying to get their own custom profiles machined. The problem was, nobody knew exactly what Armstrong had done. The pressure angle, the tooth depth, the root radius, these were all variables that had to be precisely matched to work properly. Teams that tried to copy the concept without understanding the engineering often made things worse. One team actually lost power because their pulley profile increased belt wear so dramatically that the belt would stretch and slip even more after just 2 runs. Nan Armstrong later revealed that the development process had cost him over $30,000 of his own money. He'd destroyed dozens of belts and at least 6 sets of pulleys during testing. He'd also blown up 2 engines when early prototypes had gripped too well, causing the blower to overspeed and explode. One of those explosions had embedded shrapnel in the shop wall that's still there today. But those failures taught him exactly where the limits were. And the pulley innovation triggered an arms race in top fuel technology. If something as simple as tooth profile could unlock 300 horsepower, what other overlooked details were costing teams performance? Crews started examining every component with fresh eyes. Valve spring technology advanced dramatically as teams realized that spring harmonics were costing them RPM. Connecting rod designs were revolutionized when someone figured out that aerodynamic drag on the rods inside the crankcase was consuming 50 horsepower at 8,000 RPM. Even something as basic as header-collector merge angles got the scientific treatment. And then by 1993, the NHRA had updated its rulebook to include specifications for supercharger pulley profiles. Not to ban Armstrong's innovation, it was too late for that, but to standardize it so that all teams had access to the same technology. The new rules specified the tooth profile, the materials, and even the surface finish. Armstrong's advantage was gone, but his legacy was cemented. He'd shown that in racing, the biggest advantages often come from the smallest details. And the horsepower wars that followed were staggering. In 1991, before Armstrong's pulleys, the best top fuel engines were making around 2,200 horsepower. By 1994, with optimized pulley profiles and the innovations they inspired, teams were pushing 3,500 horsepower. By the end of the decade, 5,000 horsepower was the baseline. Today's top fuel engines make over 11,000 horsepower, a number that would have seemed like fantasy in Armstrong's era. But you can trace a direct line from those modern monsters back to a machinist in Louisiana who looked at a pulley and saw something everyone else had missed. And Armstrong's custom pulleys also changed how teams approached the entire drivetrain. Once they could reliably transmit 2,500 horsepower through the belt drive, other weaknesses became apparent. Crankshafts that had been adequate at 2,200 horsepower started breaking at 2,500. The harmonic dampers couldn't control the increased torsional vibrations. Even the oil pumps had to be redesigned because the increased bearing loads required more oil pressure than existing pumps could provide. The financial impact was significant. A set of Armstrong's custom pulleys cost about $2,000 to manufacture, expensive, but nothing compared to the advantage they provided. Teams that had the pulleys could demand higher sponsorship fees because they were winning more races. Armstrong himself became one of the highest-paid crew chiefs in the sport, eventually moving to Don Prudhomme's team where he continued to innovate. His next breakthrough involved using acoustic analysis to identify combustion inefficiencies. But that's another story entirely. There's something beautifully pure about Armstrong's innovation. In an era when top fuel teams were spending millions on exotic materials and computer simulations, he found 300 horsepower in a part that cost less than a good set of tires. He didn't need a wind tunnel or a supercomputer. He needed an understanding of mechanical engineering and the patience to test dozens of iterations until he found the right one. The pulleys also demonstrated a fundamental truth about racing. The rulebook only restricts what it specifically addresses. Armstrong didn't break any rules because there were no rules about pulley profiles. The NHRA had never thought to regulate something so seemingly insignificant. This lesson wasn't lost on other innovators. In the years that followed, teams found advantages in areas the rulebook had never considered: the surface texture of clutch discs, the resonant frequency of intake runners, even the thread pitch of rod bolts. Jonas Armstrong retired from top fuel racing in 2014, but his pulleys are still spinning on drag strips around the world. The modern versions are made from aerospace-grade aluminum with surfaces treatments that Armstrong could only have dreamed of. But the basic tooth profile, that 14.5-degree pressure angle with the deep engagement, remains largely unchanged from his original design. It's a testament to how right he got it the first time. In interviews years later, Armstrong was asked if he'd ever considered patenting his pulley design. He laughed and said that by the time a patent was granted, everyone in racing would have already copied it anyway. Besides, he said, the real value wasn't in the pulleys themselves, but in understanding why they worked. Once you understood that, you could apply the same thinking to any mechanical system. Find the loss, understand its cause, and engineer a solution. It sounds simple, but as Armstrong proved, Simple solutions to complex problems are often the hardest to find. Nornen, the story of Dale Armstrong's pulleys, is more than just a tale of racing innovation. It's a reminder that expertise can come from unexpected places. Armstrong's experience with industrial conveyors gave him a perspective that pure racing engineers lacked. He could see the problem differently because he'd solved similar problems in a completely different context. In a sport that often promotes tunnel vision, his outside perspective was worth 300 horsepower. Today, when top fuel teams are chasing advantages measured in single-digit horsepower gains, Armstrong's 300 horsepower leap seems almost impossible. But it happened. And it happened because one mechanic refused to accept that belt slip was inevitable. He questioned an assumption that everyone else took for granted, and in doing so, he changed the sport forever. The next time you watch a top fuel car launch off the line, accelerating so hard that the driver experiences over 5 Gs of force, remember that some of that violence can be traced back to a Louisiana machine shop where Dale Armstrong spent long nights cutting metal and measuring teeth. He didn't just outsmart the NHRA rulebook, he outsmarted an entire industry's assumptions about what was possible. And he did it with nothing more than a different way of looking at an old problem. In the end, that's what separates great innovators from everyone else. They don't just see what is, they see what could be. Armstrong looked at a slipping belt and saw wasted potential. He looked at a rulebook and saw opportunity. He looked at a problem everyone had accepted and decided to solve it anyway. 300 horsepower hiding in the teeth of a pulley. Sometimes the biggest breakthroughs come from the smallest places. You just have to know where to look. What's the most clever racing innovation you've ever heard about? Drop a comment below. And if you enjoyed this deep dive into drag racing history, make sure to subscribe, because we're just getting started with these stories of engineering brilliance hiding in plain sight.